All right, folks can see our slides, I think, so we can get started. Okay, so my name is Phil Honenberger, and I'm happy to announce the start of CEAMLS's Lunch and Learn series. And the idea of this series is really to showcase research from Morgan's excellent CEAMLS faculty, which are housed in particular departments, but also have a research appointment with CEAMLS, and their research staff. And there are about, I think, a dozen of us. And so over the course of the year, you're going to hear from each of these members of our team about recent research. And another part of this series, part of the framing of it, is that we're going to invite people from other institutions or from Morgan that work on similar topics, or that we have ongoing collaborations with, to give short talks as well. And so the idea is 2 short talks, 20 minutes each, followed by 20 minutes of Q&A for both speakers. And for those who are here in person, serve some lunch as well. And so we'll be done by 1 o'clock. I'm going to speak for about 10, maybe 15 minutes tops, and then turn it over to Dawn to talk for 20 minutes, and then we'll have 15 to 20 for the Q&A. So the research that I'll be reporting on is co-authored with Gabriella Waters, which many of you know. She's kind of I'm going to try to speak to the in-person audience, but people online can hear me too, I'm sure. So sort of a superstar and a veteran of CEAMLS. She's moved on to Virginia State University, but we were starting to work on this topic of biases a year or 2 ago, and happy to have seen a paper come out in Archive first and then in Frontiers in Big Data just recently, which we think really reframes the idea of AI biases in a more productive way. So I think this audience is familiar with the idea of AI systems being biased in one way or another. Sort of classic case, just to take one case, was the COMPAS controversy. Classic example, a recidivism prediction algorithm, which is used to decide how likely an individual who's brought into the criminal justice system with a charge is to be charged with another crime within the next 2 weeks, or excuse me, 2 years, was found to have higher false positive rates for people of African-American or African background in comparison to Caucasians. So this seemed to like a pretty strong indication of bias. Unfairness, discrimination, these are often kind of synonyms in terms of this use of the term bias. And there are lots of other examples of this in AI and machine learning systems. And so what we wanted to do is kind of step back for a minute and ask, like, well, what is this thing bias? How could we define this, right? And something that comes up in that domain is a phenomenon that's talked about by cognitive scientists and by statisticians, that bias is not always bad. Sometimes you actually want some bias, or bias is preferable to alternatives. And so there starts to be a discussion in this literature about how bias is not always a bad thing. There's even a paper from 23, Why We Need Biased AI, how including cognitive biases can enhance AI systems, where they're very positive about the idea of biased AI. And so when you compare this to the kind of like classic understanding that biases must be either errors or unfair in some way, then you have a paradox, right? So how can you both say biases are good, but also say biases are erroneous or unfair, right? So how do we sort of square that circle? And our answer is, well, look, they are sometimes erroneous and sometimes unfair, but not always. We need a definition of bias that does not assume that bias is bad or bias is erroneous. And then we have to recast our understanding of what AI bias is so that it includes both the good or acceptable biases and the bad or unacceptable biases. And just to give you some examples of like well-known cases where bias is not too bad, we have this phenomenon of bias variance trade-offs in machine learning. So if you think about a prediction system, something, a system for making guesses about some like data where you don't actually know the system in full. You're making guesses about something that you don't have full knowledge of. That's something that machine learning is very, very good at, developing systems that do that. But such systems are often erroneous, almost always erroneous to some extent. And so their error can be thought of as coming from different places. One of the places it can come from is bias, and one of the places it can come from is variance. So variance is basically like undirected errors, and bias is some kind of directed error, okay? And so it turns out that there's a trade-off between these things, such that if you have, sometimes if you have a little bit more bias in your system, you can reduce the variance and reduce the overall error. So in those cases, it seems like bias is actually recommendable. So this is an example of the kind of thing that these authors, Hagendorf and Fabi, really emphasized when they were saying we need biased AI. Okay, just that's one example. Another is inductive bias, which is just the phenomenon that when you're making guesses about things you don't have full knowledge of, you have to make certain assumptions, and you could have made different assumptions. So the fact that you make some assumptions rather than others is a kind of bias. Okay. And if you don't make some assumptions, you won't be able to make a guess at all. So since you have to make some assumption, you have to have some bias in order to be a guesser at all and to do a good job at guessing. So those are some of the examples. Now, when we come to this question of what is AI bias, people have offered a number of definitions. Banks in London have this very nice, simple definition. It's deviation from a standard. I like that, but I can think of cases of deviation from a standard that pretty clearly don't count as biases. Like, say that people are trying out for a varsity football team and they don't make the cut. They deviated from a standard, but is their performance biased? I would just say it's, subpar or something like that. So we really like this definition from Kelly, and we think it's very useful for kind of having a neutral definition that can capture and help us navigate both the good biases and the bad biases. And when you boil it down, that definition is basically biases are asymmetries. There are cases where you have, across comparison across, say, two groups or two parts of a data set or two possible ways of doing things, you have some favoring of one over the other, or you have some, higher content in one place than in another. Now, that already kind of should suggest to you that there are going to be many cases where you want bias in systems, because, for instance, suppose you want a prediction system and the thing you're trying to predict, it's very unlikely to be perfectly symmetrical. And so you're going to want your AI to be biased in a way that corresponds to the thing you're trying to predict. In other words, you want it to be asymmetrical too, to match that thing, to be. So interestingly there, your system will be symmetrical by the standard of comparing the system to the reality, but it will be asymmetrical in terms of the structure of the data that is describing that reality. Okay. So I'm kind of going on a little bit into what are the implications of this view, but this is something we do in the paper. So like the next two questions for us are, why is a bias bad when it is? How can this bias as asymmetry view help us to answer that question? And what should be done about biases of different types? Yeah, so you got a question?
Is this more like a lecture type, or is it interactive?
Yeah, you could ask one question. That's fine. Yeah, we could do one or two. Yeah. We save some period for Q&A at the end. We don't want to cut into that too much, but yeah, what's your question? Just like clarificatory question. Yeah, what's up?
Yeah, not really like familiar with like the new AI technology. What to learn from this presentation?
Well, this is about bias in AI. So a lot of people will say we want unbiased AI. We want to remove biases from AI. We think if you think harder about it, you see that AI systems have to be biased in order to do the things that they do well. The issue is some of the biases that they have, we definitely don't want. So we don't want biases that involve, differential treatment of different demographics for no good reason, right? We don't want a AI algorithm that disproportionately harms a certain demographic where there's like no reason for that besides just the way it was trained or something. But we want to get clear
really
about
hear
what
the questions in the room, by the way. So
you could not hear that.
We could not. So if you could repeat that, that would be great. But from your answer, I think what you're describing, or to the person who asked the question, is how this demarcation, like if there's a line of demarcation where a pendulum would swing in one direction or another, and if it goes too far in one direction, it unbalances the system in that direction. That level of asymmetry is what we're describing here. And when it unbalances it in a way that produces harm, then that is a negative asymmetry versus a beneficial one.
Yeah, that's really helpful. I mean, the question was just what can I hope to learn from this presentation as someone who doesn't know a lot about AI? But yeah, I think that's helpful as well. So thank you. Yeah.
I didn't see some comments in the chat. I'm not sure those are questions.
Let's see. Please repeat the questions. Oh, Don Wunsch says, Don, do you want to make your comment real quick? You want to unmute and make your comment rather than have me read it? I think you'll do better justice to it.
Well, you can read it if you want to read it, but basically there in orienteering, you might go left or right on purpose, and that way on your next step, you'll know which direction to go.
Oh yeah, that's interesting. Yeah, so that's a case of inductive bias, would you say? Or yeah, interesting. All right, so good stuff. So I will just proceed on and get done in the next 4 minutes, basically. So a big part of our paper does this thing that a lot of papers, review papers in particular about AI biases and bias mitigation do, which is we look at the whole AI ML pipeline from conception of an AI or ML system, the choice of a model, choice of training data, the training process, then the model that results, and its outputs, correlated to various inputs, and then what's done with those outputs, decisions that are made on the basis of that. Okay. And so you can think about that as kind of capturing, like from start to finish, everything that's involved in developing and using one of these systems. And there are biases that can be introduced at different points in that pipeline. Well, we can see each of those biases as a type of asymmetry. And some of those asymmetries are benign or even necessary or recommendable, and some of those asymmetries are problematic. So I'll actually not go into this in detail because you can look at the paper if you're interested in it, but I will say that we think that biases are bad when they are, because they do one of these three things. Now, it doesn't necessarily mean that you won't sometimes take the hit of that bad thing, because taking that hit is still better. You're better off than you would be if you didn't. So sometimes it might be okay to have a system that's erroneous a little bit, or that deviates from ideal processing in one way or another, right? Because it has other benefits. But the basic point is biases are bad when they are for one of these three reasons, or more than one of these three reasons. They increase error. There's a deviation from some kind of processing ideal, like an idea that when you are making a decision of this type, you ought to follow this rule, and the system deviates from that, or that it treats people unfairly somehow. Okay. And so we have a nice diagram in our archive paper that lays out what those three types of problematic biases are. And then in both papers, we have this like lengthy discussion of throughout the AI ML pipeline, where biases of different types show up. So an interesting thing about inductive biases, this will be my last point I'll leave you with, okay? Because I've said sort of what the problems are with some of those, where problematic biases can come in. And those, like, we want to mitigate, correct, fix, right? And there are a variety of tools for doing that. But what about these cases that people like Hagendorf and Fabi had said were benign? Okay, like in particular, inductive bias and bias variance trade-offs. I want to make a couple points about that, because I think in a way they might have oversold the benefits of bias a little bit. So here's how I would put it. About inductive bias, right? Inductive bias of some kind is necessary, but that alone doesn't tell you that the particular inductive bias that you adopted was a good one. Sometimes a particular inductive bias you adopted will do good things for you. Sometimes it will steer you way wrong. So it's really, really important what the content of that is. You wouldn't want to say the way to fix AI or make AI better is just pour a whole lot more inductive bias on it, right? You need to know which inductive bias you're selecting. And then likewise about bias variance trade-offs. This is an interesting part of the paper, incidentally, where we kind of break down in data, different types of bias in data, because there are so many different types, which really are different kinds of asymmetries, some of which are acceptable, some of which are unacceptable. But the other issue is about bias variance trade-offs. Really, yes, it's true that introducing more bias can reduce variance, but it's really only a relative goodness of the bias. It's only good insofar as it reduces variance and thereby reduces overall error. It's not like intrinsically good, because it's still an error. And if you could find a system that had both lower variance and lower bias, you would be better off. So again, it's not a case of like just heap more bias on your AI and things will be better. It's like, and furthermore, yeah. So anyway, so I think that's enough. Thanks a lot for taking the time to share in these couple of thoughts from our research. And I look forward to hearing more from Gabriella, especially during the Q&A. And very glad that she could join us today. And with that, I'll turn things over to Don
So we do Q&A at each talk or after the session?
I think we do it after the whole session. That's the plan. So it's 20 minutes talk, 20-minute talk, and then Q&A for both of us. Is that all right?
Might use some of the thoughts people make.
All right. Don, you want to let's do 5 minutes Q&A so we give Don plenty of time. So 5 minutes Q&A and then Don will take over. Is that okay? All right.
So I think a lot of times when people think of the bias variance trade-off, it's simply in normal performance. So you're looking at bias as indicative of the error in the training process. As you're kind of minimizing your loss function, that is indeed the bias that you'll see when it gets down to zero, but not quite down to zero, because if you do, then you have an overfitting system, which doesn't perform well when you have data that has been seen. So in that framing of bias and variance, which sounds different than asymmetries, how do you connect the two? Like those items?
Yeah. I wish that I should have asked Kofi to come up because he had not just a question, but like a lengthy comment and contextualization. Though, but I will try to summarize your point. So I think the point was that in the context of training and machine learning, you bias in bias variance trade-offs, usually bias is used to talk about like the value of stopping before overfitting, basically. And so how do you make sense of that as an asymmetry? Yeah. I think it's that anytime you stop before overfitting, you're treating some data points in your data set differently than others, right? And you're not treating them all. I mean, so there's some kind of asymmetry in terms of how the algorithm is handling the data that it's trained on. And I think that's the way to characterize it. Yeah.
Well, I think
Like, so say that there's a bias towards, setting values close to 5. So everything gets like pushed closer to that particular value and, n equals 5, y equals 5. Okay. Then the data points that are far away from 5, right, are getting treated very differently than the data points that are close to 5. So that's a kind of bias in the performance. I'm talking too much. That was not helpful, maybe. Yeah, go ahead. Go.
no, I mean, so this could also be a question that Gabriella may want to address as well. If I treat bias from the standpoint as noise in data, so really what I'm trying to do is make sure that I get as close to a well-trained system that doesn't overfit on noise. Then I'm getting to zero bias, but not quite zero bias, because at zero bias, I'm overfitting, I'm learning the noise in my system.
I see. You want to get bias as low as possible, but not to zero. But I do think, on the other hand, it's not so. I don't think it's that you want to get bias as close to zero. It's just you want to get it low enough, but not too low, right? Is it that you literally want to get it as close to zero as possible without reaching zero, or is it just
in the
there's a
traditional sense of bias?
yeah? Okay.
From that perspective.
That's interesting. I mean, the graphs from like that 1992 NeurIPS paper that introduced the bias variance thing, they show you the trade-off, right? And so around a part of the curve, right, bias goes down, variance is going up. Bias is going down, variance is going down, total error, right? There's a point at which you want more bias, and it's not just as close to zero. There are a few values in there's some range, right, within which you're better off having some bias than no bias. I think there are sometimes, in other words, my point is there are sometimes greater than like the limit of zero values for bias that are preferable to limit of zero.
So if I could jump in just for a second there, I think part of this is challenging because what you're trying to describe, Kofi, is an automation for not suppressing all differences, but also distinguishing between benign and problematic asymmetries. And because this approach is new, there is no automatic way to do that. Can we develop it? Wink, wink, yes. But I think that's kind of what you're describing.
That's fair. It's essentially an area of research to think of how to frame those traditional ideas of bias as error in the idea or the framework of asymmetries.
Yes,
That's what they're saying.
yes. And
All
you
right,
know,
this is
I love a good problem. So if we want to explore that further, I think that's a place to deepen the dive in terms of now that we've identified that these asymmetries exist and that some of them are problematic and some of them are not, and for the reasons that they aren't. So that now when we are looking at how we treat the noise and the loss function with this in mind, this is an area that we can expand on in our approach to development.
right. Terrific. I think, ooh, let's see. Yeah. Let us turn things over now to Dawn, who is going to speak with us about all kinds of cool things. Dawn and I have been in a running conversation for about a year now, maybe a little more than a year. We've had a grant proposal together. We probably will reapply on that proposal. And I've always really enjoyed talking with Dawn about his work and his thoughts on AI. So I'm turn things over to him.
Yeah, thank you very much for pulling this together, Phil, and thank you, folks. It's good to hear Kofi's voice, and look forward to seeing all of you again. I have a soft spot for Morgan State after having visited there a couple times, and your dean is a member of our board of trustees and a close friend of our chancellor. So anyway, there's a lot. Please say hi to him for me, to Oscar Barton. I know you come from different departments, but your Dean of Engineering is very closely aligned with our university, and we would like to leverage that relationship further. So it's been fun to visit you before, and I look forward to doing so again. I've looked at the paper that he mentioned and had some communications with Phil about this. And so with a little bit of knowledge can be a dangerous thing, but I think that some of the stuff that we do, that we're known for here, has the potential to be of some help. And so we're especially known here in my group at Missouri S&T for unsupervised learning and reinforcement learning. And the flavor of unsupervised learning, we work in all areas of unsupervised learning, but the flavor of it that we're best known for is work with adaptive resonance theory. And so I have many intellectual heroes, and one is Steve Grossberg, who came out with his magnum opus in about 2020. And I quickly built a course around this, which I'm going to offer for the second time next semester. First time I offered it right away in 2020, based on this book, which I recommend very highly. Conscious Mind, Resonant Brain. And adaptive resonance theory is a theory. It's not just a neural network architecture. And some people who've heard of it, maybe played with it a little bit, make that mistake, but it is a theory about how learning happens in all kinds of brains, not just human brains, but animal brains as well. Yeah, I would argue even down to insect brains. And it's motivated by the problem of unsupervised learning. In other words, if you learn something and you need to correct as you go, how do you do that without a deus ex machina, without some kind of intervention, whether an engineered one or a divine one or a human in the loop? And so it's important for unsupervised learning, but as I'll mention, it's useful for other learning modalities too. And I've written about several engineering advantages of using it. I'll talk a little bit about that right now. And so adaptive resonance theory is a competitive approach in the recognition level. It includes neurogenesis, so you can grow more neurons for dealing with the corrections that you need to make, but not only by neurogenesis. There's another very important mechanism I'm about to say. It's an incremental learning method, but it's a fast learning method. And I've already mentioned it was designed with unsupervised learning in mind. But now I want to say the core piece, and that is reset and resonance are key. So the reason it resonated for me is that, like many of you, I'm an engineer, but I also started out in applied mathematics. And so if you took math through differential equations, you would have encountered resonance in differential equations models when there's some feedback. If you took physics through, say, a second semester of physics, you would have encountered it. They might have shown you a video of the Tacoma Narrows Bridge. If you like music, you might have encountered resonance in the beautiful notes of, say, a harp, or the way certain harmonics are played on a guitar. Um, and one of my favorite examples is Ella Fitzgerald singing during certain Super Bowl commercials and shattering a wine glass with her voice because her voice could hit the resonance frequency of the wine glass. Well, what's bad for wine glasses and bridges that are designed at the wrong frequency that the wind are blowing through the canyons, uh, what's bad for those things is good for music and it's good for our brains. Because when you say blow your mind, it does not literally blow your head up, but it means that you're driven towards a decision. So resonance is viewed by Grossberg, and I agree, as something that is important for fast learning, that is important for entering a state where learning gets burned in. It's important for decision. But equally important is the ability to disrupt the resonance, and that's what reset is about. So something that allows you to disrupt the resonance. So I'm showing here a neural net architecture where there's a path for reset and resonance, and reset just disrupts the resonance. And this is a cartoon of that at work. And we don't have a lot of time to go into it, but I do want to say also, as I mentioned before, that there's a supervised version. So you can have a system like the one I just showed you. You can have another system just like that for the supervisory signal, but you're forming clusters of that, and then you have another system that negotiates between them, and you can do supervised work with this as well, and that opens the door to many other things, and one of them is something I'm going to talk about. But I'm going to give a little digression and say I'm going to mainly talk about simple things, but we do fancy things with this as well. So this is from a DARPA contract that we had a phase 1 that I was PI of. The phase 1s were encouraged to marry. We married with Teledyne Scientific. The Teledyne is also the company that acquired FLIR about the time that we worked with them. And these are the individuals, Mario Aguilar-Simon and Andrew Berna were the ones we worked most closely with. And in the yellow and purple task, these are things that we were responsible for helping with. And we were using adaptive resonance theory to do that. And I'd love to say more, but I just want to say this stuff has been worked into bigger and fancier systems. But now I'm going to step away from that for a moment and come back to it. Because I said that adaptive resonance was a flavor of unsupervised learning, and I said that we work in many flavors of unsupervised learning. And this book I published with my doctoral student at the time, actually as a postdoc at the time, Rui Xu, called Clustering. And so what you do when you're doing clustering is you have your data, you look for features in the data, you have a menu of algorithms and the design of algorithms, and this is where you see most of the work in the field, but then you need to do validation, interpretation, and get to knowledge. And these parts have humans in the loop. And this part often has human in the loop, but not always. And this is a lot of the importance of the field. And I think an overlooked importance of the field, but still it's an area that people do a lot of work in. They publish a lot of papers in it. It's chapter 10 of our book is devoted to this. But things have moved forward a lot since the time of the book. And that's what I want to talk about because I think it's relevant to this issue of asymmetry that Phil raised, that Phil and Gabriella raised. So incremental cluster validity indices. This is something that was an outcome of our DARPA project. So my elevator speech to the DARPA folks was, hey, before the DARPA project, you should run your clustering algorithm and pray, because you would only find out in non-real time after you did it how well you did, and you had to do this menu of approaches, and I'll show you a little more about the menu of approaches. And you could not find out as you were doing it. You'd have to find out the good news or bad news after you're done. And even then, it was computationally expensive. So slow, popular, but slow. It's still popular and it's still slow. But these real-time methods are superior. They dominate the other methods. There is no reason to use the old methods. That is outmoded now by this contribution. It's not only us. We got inspired by work of Jim Keller and Jim Bezdek, and they had a few of them, but we came up with more of them. We talked about performance guarantees. And this is a family of cluster validity indices that are not incremental. These are the old ways of doing it, but but you have a menu of quite a few of these. And this is just a handful. We have a bigger group of them. So this toolbox, there are all versions that are non-incremental, and these are incremental ones. And so roughly half of them were along before we came along, and we fleshed them out and gave more of them. And there are more still now. I'll call, and my WB stands for within and between, and NI stands for neg entropy, which is an information theoretic approach. These are two I'll talk about some more later, but they're all good in their own way. They all have their different strengths. And so, for example, the Con index came out after our book came out, but we use it a lot. So incremental versions, what they buy you is they allow you, as each data point comes in, you update your value of your index. And so that's what the animations are showing, that you can do this. And it's great that as you go, you get to where you're pretty good. You got one more data point and you update, well, how are you performing? Is that making you perform worse because of the way you classified that data point? Or are you doing better? And you can do this in the space of unsupervised learning. And one thing I might as well say while I've got clusters up here to look at, what you would like to have when you're doing unsupervised learning. So unsupervised learning is kind of a bad news situation in the sense that if you had an oracle, you'd do supervised learning. If you had something telling you always the right answer. Or if you had at least a cost function, then you can take derivatives with respect to that cost function, and you got a signal for your gradients and backpropagation. You can reduce it to what you would do if you had that oracle. And in unsupervised learning, you say, forget all that. I don't have that. And you may have some hints, but not to the point where it would translate, like winning or losing a game, and you play a lot of games. That's not quite a cost function, but it might as well be. You can treat it just like reinforcement learning. But if you don't have enough to do that, then what do you do? And one thing that you can always do is you can say, well, I'd like my clusters, if my point is in this cluster, I'd like that to be really in there. I'd like this one to be compact. I'd like it to be W within. And if I say that it's in this cluster and not this one, I'd like the between distance to be big. And so you can do a sum of squares, and that's the WB1, but there's a lot of ones that do something like that. And if you want to know more about them, read chapter 10 or read these papers I'm showing you. So this is something that's very valuable to be able to do this as you go. And even if you stay back in the battle days and you wait until you're done, you're going to run a couple orders of magnitude faster in executing these. And again, here's the neg entropy one right here. Here's the WB one here. We'll talk about more later. But these run a lot faster because they don't have to save all this; they accumulate it. And so this is something that we've contributed to, but what and I did that with Nick and with Leonardo. I'll show you their pictures later. But one great idea that Nick came up with was to leverage how these different ICVIs behave, because some of them are better at telling the difference when you're over partitioned, when you have too many clusters. Some are better at telling when you're under partitioned. And so he fused them. And that has worked great. Here's a cartoon of that. And so you take your old data and you train a classifier, and this is just a supervised trained classifier, but on a lot of examples that you've seen before, and you fix that. But then you have these ICVIs that are running when you're just clustering, so you're doing unsupervised learning. You don't have any feedback about this, but you do know which of the ICVIs are good at detecting under partitioning or over partitioning, and you have a classifier telling you which one you should believe more. So like a mixture of experts, and these work great. So here's a confusion matrix from that journal paper, and so this is an example of something that we can do for that particular problem, but it could have a goal of asymmetry instead of under partition versus over partition. So that's kind of the takeaway here. But another thing, I want to bring back art now, because that was just ICVIs. But so we realized, all right, we had this good news to share about ICVIs, and we think everybody should use them. If you're doing unsupervised learning and you're not using them, we think you're using something old-fashioned that is outdated and dominated by these methods, and they're not hard to use. They're easier to use. They take less compute cycles. We have shared how to use them. You're far better off using them. So even if you don't care about any of this other stuff, that's worth using. But we said, all right, well, if that's so great, one thing might be, how about using what you learned from that to change what you're learning, because you're getting this information as you're learning. And that's what this stuff is about. These are a couple of papers about that, doing that both offline and online, because remember, I told you, even when you're offline, this is worth doing. So we wrote papers about doing this both offline on the left and online on the right. And what this looks like is, remember I showed you ArtMap, and I said that you have two clustering algorithms left to right. I'll go back up to that real quick. This one. And so these are just art units, but this one is for your supervisory signal, and then you have something negotiate between the two. But now we got rid of that one because we don't have a supervisory signal. We're back to unsupervised, but we use that idea. But instead of another clustering algorithm here, we put your ICVIs, and it'll work with your meta ICVIs as well. But this paper had it with just the plain old ICVIs. And what it does is it gets you very high quality clusters. These are pretty pictures of them. But you know, we're engineers, we like numbers. These are the numbers. So this is using neg entropy, which worked best. The within between was also pretty good, but the neg entropy beat, and it beat everything else most of the time. This dual vigilance fuzzy art, we invented it, beat it in one case. Gaussian mixture methods tied here and one here. Spectral clustering tied here, one here, and tied here. And Ward's method of hierarchical agglomeration clustering, tied here, one here, and one here. So we won most of them. And this one is one of ours, so we really won most of them. But this method is really a great thing to do when you're doing online learning. It's really a superior approach. And this is just more of the same. Other data sets, other comparatives, and here k-means won one of them. Like up here, k-means most popular clustering algorithm. Here, it didn't win any of them, but here k-means came through on, it didn't win, it tied. Okay. So, and here's within between, it showed up in some of the winners here, and neg entropy, but these are incremental cluster validity indices working together with adaptive resonance theory. So we've provided open software, open source software, both in Julia and in Python. Here's repository links. And here's acknowledgements. All these folks have done wonderful stuff. You've mainly heard today about work with Leonardo. who's now an assistant professor at University of Rio Grande do Norte in Natal, Brazil. And he stays in touch. Nick Melton is about to finish his PhD. This is mainly work in collaboration with those two. But these folks that are pictured have done important and valuable collaborations as well. Anyway, that's what I wanted to say, and I'll go back to these repository links, but I'll be sure to provide this to Phil as well. So as you can see, we have some tools, and these tools, I think they could be fine-tuned to issues about asymmetry. So like I was mentioning in the map and compass orienteering, but a lot of things like that. So I've got a paper from long ago where you're looking at investment decisions. And one thing Warren Buffett likes to say is investing is like where you're at bat, but you don't have 3 strikes, you have a whole bunch of strikes. Okay, the ball can come whizzing by right in the middle of your strike zone, no penalty for ignoring it. You can just wait until you love that pitch and you can knock it out of the park. That's how his attitude towards investing. A lot of people don't feel that way. Day traders don't feel that way, but that's how he views it. That's what I believe. So I published a paper very early where we deliberately biased the decision making because you're taking a risk. So you want a margin of safety, you want a margin of error. So we would see a bunch of pitches that went right through the strike zone and you say, no, thanks, I'm waiting for a better pitch, right? And then you see one that you really like and you hit it easily. So that's an example of a case where bias is valuable, right? And so that's why I came up with the orienteering one, thinking of something that was analogous to that. That like if you're walking somewhere through the woods and you know what you're going to do when you get to the road or the ridge, then you might deliberately bias one way or the other so that it's easy to know which way to turn once you get there. Particularly if you will soon be making another turn later. If you're about to walk, yeah.
Don, just want to say, I do want to turn things over to questions.
Yes.
Next minute.
Yes. So yeah. So I'd love to get questions, and I'd encourage questions for all the contributors, and also comments are welcome.
All right, terrific. Thank you. John, please join me in thanking Dr. Wunsch for joining us today. Any questions for Dr. Wunsch? And I will try to keep your questions brief or be willing to come up here and speak to the Zoom audience so that either I can repeat them or everybody can hear your question. Any questions?
I have a simple one.
Okay, Kofi has a question.
Number of clusters for ICEI. Do you have to predefine the cluster numbers?
Do you predefine the cluster numbers for ICI?
It's clustering algorithm agnostic. So most flavors of adaptive resonance do not define the number of clusters. And so if you're combining them with adaptive resonance, then no, you don't. But for example, they can be used with k-means, in which case you would. So it is designed to be clustering algorithm agnostic. That's a great question. Thank you for that, Kofi. And that's part of why we say everybody should be using them, and we didn't, it'd be egotistical if I said that and we were the first to come up with it, but we followed after the giant Jim Bezdek and Jim Keller, and you look them up and they were famous in clustering when I was still a grad student, so anyway, they're good friends, and they beat us to this, but then we saw it was good and and doubled down on it. So we recommend it to everybody, and we've made it more accessible.
Any other questions? Can I ask to what you would attribute the inertia or whatever of the non-online approaches? Why is k-means, a non-online k-means, still so popular? If they're easy to use and they're demonstrably more efficient.
Well, so k-means is very frequently used online. I'm talking about the step of validation afterwards. So there are clustering methods that are used offline, and you could have an offline version of k-means, and many people often do. But what I'm saying is that these validation measures are available online. And then why are they not that used? One thing is that and with a lot of uh, the value of novelty in publication and venues that get a lot of citations versus the value of efficacy uh, uh, differ culturally between disciplines and publication venues. And so basically, I'm saying that a lot is fad driven as opposed to results driven in the field. And that's fine because the research is about exploration. And so exploring things that are new and seeing what you can milk from that is valuable. And if people are a little slower to adopt something that is not as new but works great, that's okay because eventually they'll come around, and there's opportunities maybe more in the business realm than in the marketplace of ideas, in like trying to get into NeurIPS or something like that. They like a lot of math and theorems. This stuff is actually pretty simple, but it works better. So like if I were going to apply this in some automated trading system, then I might use it, not say anything about it, right? But it works, and so that's part of the answer. Is it's maybe a little bit less sexy, and I'm actually deliberately trying to make it a little bit less sexy. I think the field of AI needs a little bit less of, hey, look at this sizzly thing, and a lot more of, okay, let's look at what we can design and show that it works and put it into a system that works. So I just came out with a paper where I said that artificial insect intelligent autonomy, AIIA, is maybe more promising than artificial general intelligence. Because this agentic AI, you could just do it by letting your AI do stuff, like let your AI go and buy things for you from your credit card, or let AI go and turn on some other piece of software. That doesn't mean it's a good idea, but it would not be hard to do it. But to actually design something that performs as well as a housefly in what a housefly does, the capability of insect is very limited, but how well it performs autonomously within that little capability is outstanding. And I would say much of the field has a lot to learn from these kind of limited things. So I'd like to just say I love that question, and the answer is that it if you have a customer, then you may be delighted if other people are not doing this. And if you don't have a customer and your main goal is to write another paper, if you use it and it helps you, please cite it. But if it helps you to publish your paper to be doing something completely different, even if it works worse, well, more power to you. Go ahead. Anyway, that's
okay. Thank you so much. I think I am highly motivated to make sure we don't hold our audience captive. So we are at time. I think people should feel comfortable. They may have to go on and do other things. But I think I'd also like to stay on for maybe 5 minutes and just see if there are any further questions, if Gabriella has any comments. So we're wrapping up officially now, but we'll stay on and talk for another 5 minutes if there are other questions. Question in the front, and then let's hear the questions first, and then we can hear from Dawn and Gabriella if she's still around. Yeah.
So where can I go to start to understand the concepts that are being discussed in this paper? So I kind of have No clue historical.
So the question is, where can I go to start to understand the concepts in this paper? I kind of have no clue what's going on, a feeling I often have in this space as well. So good. So that's a good question. And then we're going to take another question from the middle row there. Oh, did you have a
Okay,
question?
and I
Okay.
will. I'm gonna switch off this headset because it's about to fail.
Oh, no. Okay.
It's an older one. It doesn't have very good battery life. So let's see here.
Yeah. Well, come to more events like this. You
And
know, I think that if you're interested in AI, interested in machine learning, there's a lot of resources on the web. You know, YouTube is good. There's a lot of ways to start to get information. We do a lot of events with CEAMLS, and
If I could.
yeah,
do you still hear me?
we can hear you. Yeah.
Excellent, good. So,
Get the paper. And then put that in your favorite LLM and ask you to break it down. Okay. No, I'm serious. And whatever questions you do not get answered, you do it, go back, do it. You know, ask for clarification, dig deeper, have a whole interactive session. The knowledge is no longer accessible at these good language models.
That's a really good suggestion. Yeah, that's a good suggestion. And if
would
you
you
write out,
repeat it, please?
well, the question, Don, say thanks. So the question was, how can I start to understand these ideas? An audience member was interested, but they felt like it was a little bit out of reach. And Kofi made the good suggestion that you could take that paper and put it into ChatGPT or Claude and say, hey, give me a summary of this, and then ask follow-up questions. So we got to ask you for a copy of the paper and get that to our audience member, and we'll make that happen. You feel free to reach out to me and I'll get you a copy of the paper. Okay.
Right. I will share these slides and my Google Scholar page is more up to date than this. And also there's a paper that is only tangentially related to this. It does cite that book, but I'll give you that paper as well. And it's called Artificial General Intelligence is Nowhere Near. Artificial Specific Stupidity is Already Here. I will give you that paper too. It just came out. Yes, and I referenced Michael Jordan and sent it to him, and he read it immediately and replied immediately and said, "I love it. I agree with every single thing you said." And then he sent me a brilliant paper that he wrote, and I think I'll share that with you too, because he's got some ideas that are, you know, in kind of similar direction, but also different about. Actually may play well to your strengths. He was talking about how important economics is for interacting with AI and how that can help with fairness. And so I think you'll be very interested in Michael Jordan's latest paper they just sent me. I instantly, I dropped what I was doing and read it and replied to him how much I liked and agreed with his paper as well. So
Cool.
I'll send you, you know, there's a lot of
Yeah,
good people thinking about this kind of stuff. So
that's great. Send me the stuff, and the audience member who asked and anyone else may write me and ask for it, and I'll just pass them along. Okay. Any other?
Pass it out to all these registered.
Sure. Yeah. Great idea.
Yeah, and I'd love to collaborate. I think that what you're talking about of looking for asymmetry, if you identify an asymmetry that you'd like to look for, then particularly if you're in the unsupervised space, I think that we can start acting on that. But if you're, but even if you're not, I think it'll be a powerful way to start a conversation.
Okay. Okay. Well, maybe just one more quick comment, and then we're gonna close. Go ahead.
No, I was just stretching.
Oh, I'm sorry. I'm sorry. Okay. All right. So, well, again, thank you all for making this first Seamless Lunch and Learn, from my perspective, a very successful event. I apologize again about late lunch. Let's have one more round of applause.
Thank you all very much.
And I look forward to, you know, broadcasting these events in a similar fashion with other faculty and research staff. So there will be other faces and other research programs up here talking about what they do. More to come very soon.
Take your email now.
Thanks, Don.
Thanks.
Thanks, Gabriella.
Thanks for hosting, Phil.
Thank you. Thank you as always.
Bye-bye.